Hi everyone, my name is Hermann Kugeler with Makai Ocean Engineering, and today I'm going to be presenting a topic that we've been working on for NAVSEA called the SVACS, or SVACS System, for Subsea Vertical Cable Control. First, I'd like to give you a little bit of background information into our company, Makai Ocean Engineering, and some of the work that we do. So we are a professional ocean engineering service provider that has been in business since 1973, so for over 45 years. And over that time, we've become known worldwide for a few key technologies that we've developed. Most notably is our work in subsea cable software and hardware development. We have a software suite called Makai Plan and Makai Lay that is used worldwide by over 80% of the subsea telecommunications fleet for planning and installing subsea cables. Additionally, we are world leaders in a few other areas, including marine pipeline design. So we design a lot of large diameter, mainly high density polyethylene pipelines, such as ocean intakes, outfalls, and that sort of thing. Additionally, we have become leaders in ocean thermal energy conversion, OTEC, and seawater air conditioning, or SWAC. And both of those technologies are using deep seawater as a renewable energy source. And you can find more information on those on our website. We have a significant technical history. We have been involved in a number of SBIR projects related to subsea cables, which is relevant to this topic that I'm going to be presenting on specifically. And these SBIRs are both software and hardware development. We hold several patents for some of the DoD-funded tech that we've developed. And our key resources are kind of what set us apart. So most importantly, we have 37 employees, 29 of which hold advanced degrees, so Master of Science or greater, in the fields of engineering, computer science, physics, mathematics, and more. Next key resource for us, and one of the advantages that we have in these SBIR projects for hardware development is our pier. So our headquarters are located at the Makai Research Pier in Waimanalo, Hawaii, where we have access to both shallow and deep waters within a pre-permitted Makai undersea test range. So we use that pier and the waters surrounding it for rapid prototyping and in-water testing of hardware systems for the Navy and other clients. Our second office is in Kona, Hawaii, and this office is called the Ocean Energy Research Center, or OERC, and this is located at the Natural Energy Lab of Hawaii. And at this facility, Makai focuses on development and testing of heat exchangers, and we've recently developed an ultra-compact heat exchanger that is showing promise. It's up to 5 to 8 times more compact than state-of-the-art heat exchangers that are currently on the market for the applications that we've looked at. And finally, our third office is in Ventura, California, where we support NAVFAC XWIC and their work in the Oceans Multiple Award Contract, or OMAC 3, where we are one of the pre-qualified contractors for that IDIQ. And that is mostly, general ocean engineering services, procurement, and that sort of thing. Finally, on this slide, I'm going to talk about some of the commercialization and transition success that Makai has achieved over the years. So in 2016, we were awarded the Tibbetts Award for successful execution and transition of SBIR projects. We also have an SBA designated commercialization achievement index of 100 out of 100, which is recognized for our transition of federally funded projects to the commercial markets. And additionally, the subsea cable products that we've developed, as I mentioned above, are used by multiple government customers in addition to the commercial clients. On this slide, I'm going to be going over the Navy's challenge in addition to some of the requirements and expectations that they've laid out for this SBIR project. So the Navy has a requirement to straighten subsea vertical cables. So current subsea vertical cables are able to kite away from vertical due to drag on the cables from currents and other forces. There's not one expected transition target for this system, but instead a variety of systems that use subsea vertical cables could use this system or a variation thereof. The expectations that the Navy has laid out is they want the system developed to be compatible with legacy cable systems. They want autonomous dynamic controls, and the system developed cannot induce significant turbulence or acoustic noise. So as I mentioned, the Navy has a need to maintain subsea cable verticality during a range of their operations, and they also need the system developed to work with legacy cables that are already in use. They can't afford to replace all of the cables that they have in the fleet and in the field with new systems. The improvement that they're looking for is they want autonomous and real-time controls of the cable's shape and positioning during their operations. And they want those controls to account for drag and other forces and motions imparted on the cables during their operations. There's currently no way of actively controlling subsea cable shape. Most systems are designed to use buoyancy for their cable orientation, but there's limits to how much buoyancy can be added. The problem that the Navy has is they have subsea cables that are able to kite away from their vertical orientation within the water column due to drag. As I mentioned in the last slide, there's not one specific platform with this need. Any application that has vertical cables and they need to maintain that vertical shape could use this system or a variation thereof. The solution that Makai has developed to meet the Navy's needs is called the SVACS system, or the SVACS. And this consists of a number of thruster modules placed along the length of the vertical cable. Within these modules, there are also sensors that send position data to the main controller that then tells the thruster modules how to act in order to correct the cable shape. The SVACS does not impact the cable functionality in any way, and the specs that we've achieved with the SVACS is we're able to reduce the off vertical angle to less than 1 degree in waters up to 3.75 knots, and we're able to correct the straightness of the cable to within 1 foot displacement anywhere along the cable in water speed up to 4.3 knots. The enabling software for this technology is Makai's own proprietary software that provides real-time control of the cable shape. So on this slide, you can see the current status of the SVACS development in addition to the roadmap ahead in order to reach a TRL 8 by calendar year 2023. So we're currently at a TRL 5 where we've built and tested a single full-scale SVACS module, and we are now working on developing the full SVACS prototype with the number of modules we need for our given application and testing those peer side. In calendar year 2022, we're going to reach a TRL 7 where a full SVACS prototype will be tested on an operational system, and at the end of calendar year 2022 and into 2023, we are hoping to demonstrate the full SVACS prototype in an operational environment. We are currently in the SBIR Phase 2 base period. So on this slide, you can see a few of the key features, advantages, and benefits of using a SVACS system versus a standard vertical cable without a SVACS. So SVACS has active control of kite angle. So the SVACS is able to maintain cable verticality within less than 1 degree at water speeds up to 3.75 knots. And it's able to control cable displacement of less than 1 foot along the cable length for water speeds up to 4.3 knots. And again, without a SVACS system, the cable is able to kite away from its vertical orientation depending on the currents and applications. Control, so with the SVACS, we have active control using electric thrusters versus standard vertical cables have no control and have completely passive systems which just use typically buoyancy to maintain its shape. The SVACS system is able to account for changes within the water, including currents, and without a SVACS system, the vertical cable shape is affected by those currents. So big takeaway here is the SVACS system provides active cable shape control and thus improving cable positioning and shape and the ability for the cable to account for drag induced on that cable by outside forces. So in order to transition the SVACS system into the Navy's fleet and take this beyond a Phase 2 effort, we will need additional funding to certify the SVACS for use on operational subsea vertical cable systems. We're also looking for support in that transition process for transitioning onto an operational system. Related to that note, we are looking for transition advocates. We're looking for a primary transition advocate for subsea vertical cable applications. And we're also, looking for other transition advocates for secondary applications. Perhaps it's not a subsea vertical cable, but you would like to maintain, the shape of a cable that's not completely vertical. Maybe it's a horizontal cable shape. A variation of our system could also be used for that. So here's where some of you that are listening might be able to help us. We do need help in transitioning the SVACS system into the Navy's applications, in addition to some other applications that you might be thinking of. So we do need input from program offices in order to transition the SVACS system onto legacy subsea vertical cables. So please reach out if you work within those program offices and are interested in discussing. Additionally, we're interested in working with program offices and partnering with prime contractors for use of the SVACS system on future subsea cable applications that require that precise shape control that the SVACS provides. Additional funding will also be needed in order to transition the SVACS into other applications. Other transition paths that we have identified, again, it's not extremely limited. The SVACS or a modification of the SVACS could be used for a number of subsea cable applications that require that precise control of cable shape. So if you have any other transition path that the SVACS might be applicable for, please reach out. I'd love to hear from you. Thank you for taking the time and sitting through my presentation. I do appreciate it. I ask that you please reach out to discuss your needs. If you have a project where you might be able to use the SVACS, I'd love to discuss. I will be available during the conference in the virtual booth, so feel free to visit me there and chat. I've also provided my information below. Again, my name is Hermann Kugeler. Please reach out, send me an email, give me a call on my cell, shoot me a text. Happy to talk. Thanks.